A very good morning to each one of you present here. ISA-VIT is proud to present another interesting technitude before you. Today's topic is Introduction to PCB Design and Electronic Design Automation. For those of you who don't know, we will look into how Eagle CAD, a free software, helps PCB designers create schematic diagrams, component placements, and PCB routing, etc. We will look into the methodology using which a schematic on your paper can be converted into a PCB layout, and the participants will also get access to all the libraries required to create their own preferred layout at their own convenient time. Today's session will be delivered by our core committee member Anirudh Pandey. Anirudh is a second year student pursuing ECE in VIT. He is deeply interested in PCB designing, hardware electronics, and avionics. I request all the participants to not unmute during the session as it will interrupt the speaker. If you have any queries, you can either write it in the chat box or ask during the end of the session. Over to you, Anirudh.
Okay, so hi everyone, good morning. I'm Anirudh and I'm a core committee member in ISA-VIT in the IoT and the design domain. So as you know, today's session is going to be about PCB designing using the Eagle CAD software. There are also other softwares available like Proteus and EasyEDA which you can try out if you want. But today I'm going to do it in Eagle CAD. So before we get into the design part, I have a short presentation on what a PCB is. So just let me present my screen. Okay, is the screen visible?
Yes, it is visible.
Okay, so I'll get in. This is going to be a short PPT. After that, we'll get into the designing part. So most of the technology and electronic products we use today would not be possible without these PCBs. As you know, if it not only help in reducing the size of the electronic product, but also help in making it cost effective. So basically, PCB is a platform which mechanically supports and electrically connects all your components which you place on it. The base of the PCB, as you can see in this small PCB, the base of the PCB is made of a substrate such as fiberglass reinforced epoxy resin, and the conductive traces, these yellow lines and all, these are made up of copper tracks which electrically connects all the components. So a few components of the PCB, like as you can see, there are two pads mentioned over here. Now pads are basically where all your components are placed. There are two types of pads: through-hole pad and an SMD pad. SMD is short for a surface mounting device. I'll talk about these two in the next slide. Now, when you place your components on this pad, you connect them using tracks as per your design. Like whichever design you're making, the CAD will be connected via copper tracks to each other. Now, after these, there are vias. Now, vias are basically small holes which electrically connect your top two layers, like top and the bottom layer. Uh, After via, we have a silk screen. Now, silk screen is a layer printed on a PCB towards the end of the manufacturing process. It helps us identify which component should be placed where and also to print any text or logo on the PCB. Now, a layer of solder mask is also applied to protect it from oxidation and exposure to dust. This layer also gives the PCB its typical green color, but also the PCB is coming now different colors because of the different components used in the solder mask. I'll go to the through hole and the surface mount. So basically, when you simply put a hole in the PCB and insert the leads of the components and solder it, they're called the through-hole components. As you can see in this photo, all the top components are through-hole components. And an SMD is the device which is simply mount on the surface of the PCB, which is soldered on the surface. So when you solder on the surface, you can actually reduce its size quite a much. So like it's quite effective this way. Now, see, before making a PCB, you need to test out your circuit to see if the design is working or not, giving the desired output or not. So you got to test it before sending it to the manufacturing process. You can do this testing via solderless breadboard, a perf board, or a strip board. I'll give a short intro of what these boards are. So a solderless breadboard is where you insert all the leads of the component and the internal connections are made on the board. So here's the internal connection photo of the solderless breadboard. So these two tracks are connected internally vertically. So all these pins are connected over here, and the horizontal pins are connected in this way. So your main components are placed on these pins, and the power connections are made through these two pins. Now a perf board is simply has an array of holes in it in a 0.1 inch grid, and it is usually used for prototyping. On the boards, all the components are soldered underneath the structure. As you can see over here, for prototyping, all these boards are used. And a strip board is more like a general purpose PCB, and it has strips of copper tracks running underneath it. So you need quite a skill to actually develop these boards and the layout to work with the strips on the strip board. So as now we have a general idea of what a PCB is, I'll get into the designing part, like the main part of the session. So I have already given the link to download this software in the chat box, and also to the libraries which I'm going to use. So I'll show you what our end product is going to look like today. So this is schematic of a voltage booster circuit. Now, before explaining the schematic, I'll explain you what the basics of a voltage booster. So this is a very primitive design for a voltage booster which I've made. So voltage booster is simply a circuit which boosts your voltage on the cost of the current. So if you provide a voltage of say at least 10 volts over here, I'll run it and show you how it's going to boost the circuit. As you can see, the voltage is increasing a lot on the output one, at least 99 volts. So basically we have a voltage which we need to boost, an inductor. This is a MOSFET, a clock signal which we need to give to the MOSFET, a diode, a capacitor. So the basic functioning is like the inductor. The main voltage is going to be from the inductor. The key principle is that the driver boost converter in the tendency of an inductor to resist changes in current by the increasing or decreasing the energy stored in the inductor magnetic field. So like this clock signal is being provided to the MOSFET. So the circuit is going to close and open very fast. And the inductor is going to resist the changes and increase the voltage on the output. So this is how a voltage booster works. Now the schematic which I have made is for an MT3608 voltage booster. Now this is an IC available. Now why we need an IC is like in the output, if there are any sudden changes in the load resistance or any ripples in the voltage given. So we need a feedback circuit to improvise over there. Like the MOSFET, this thing, the voltage, the clock signal is going to be changed accordingly, like according to the ripples and all the change in the resistance. So we need so for that feedback circuit is there in this IC. Like if we don't use an IC over here, we are going to require a microcontroller with also a lot of code. So it's better always to use an IC. And the inductor is over here, the Schottky diode is over here, and the capacitors. And these are two output and input terminals. I'll also show the board. Yeah, this is going to be our end board, which we are going to make. I'll just close this one and start off with a new one. Okay, so if you have downloaded this software, this is the home screen that you're going to get. So here are all your projects and everything that you're going to create. So I'll simply right click over here and create a new project. I'll say name it ISA. So when you right click it, first we need to create a schematic out of it. Like you can't go for a PCB designing without creating a schematic first. So this is the home screen that you're going to get for creating the schematic. It's really simple once you get used to it. I'll show you. Like here is the button to add all the components, add parts. Here's the button for the info to show, to group the components, to move the components, to mirror, rotate, copy, paste, delete, change. So these are all the simple buttons. Now I have provided the libraries. I have already shared the Google Drive link. So there are 3 libraries over here, and the other libraries which we're going to use will come pre-installed with the software. So I'll once show you how to install these libraries. So just simply open it. It's in a zip file. I'll download it. Yep. Once you download it, just go to download. Yeah, it's going to be in a zip file. So first extract it. Okay, so now once you have extracted the folder, just open the schematic. Now here you have the option of library. So just go to library, open library manager. Let's go to the available section. Here, if you are using the online version, all these available libraries will also come online. But at the moment, I'm offline working. So just browse for the libraries. Go to this folder which we have made, and this is a simple library folder. Just click it, open, and it will show over here. Now, when you click use, it will show in the in use folder. I've already installed the library, so I'm not going to do it again. Let us show you instead of that. Yep, over here. Yeah, it's duplicated for me, so I just remove this one. So this is the Adafruit library. You can do similar for the other two also. So the other two libraries are the MT3608 IC1 and a library for the Schottky diode. So first you need to add all the components in the schematic diagram. So I'll just go to add part. When you open add part, you'll get this window over here, where you can search in all the libraries, whichever component you need to add. So first I'll add the IC. Now IC is as a MT3608. So you can simply search for it, hit enter. Okay, not this one. Wait, I think I didn't download the MT3608 one. Okay. Yep. Okay, now I think we have it over here. Yep, yeah, we have it. So add part. Yeah, here you go. The IC for the MT3608. Now if we hit the right click key, it will rotate it. I'm going to put it this way. Now I'll just hit escape to again go to this window. And now what we need to add is the inductor and the diode. So I'll simply type inductor. Inductor which I'm going to use is from this library, InterNeoCell, the MS42 version. So you can simply place it over here. Hit OK, and then escape. Yep. When you type SS34 after installing the other library also for the Schottky diode, when you type SS34, you're going to get this one. I'm going to reverse it and place it over here. Hit escape. Now, okay, now we need to place the potentiometer for the feedback circuit. If I type potentiometer, no, in this instead, I'm going to use the resistor library, which comes pre-installed over here. You can see it in the resistor library. We have the R trim. So all these are for the potentiometers, different versions of the potentiometer. So what I'm going to use is the R trim 3296W1. You can place this component over here. I'm going to reverse it and place it over here. Now, if you have downloaded the Adafruit one, in the Adafruit library, or in the RUS part, you can find all the resistors of the US version. So I'm going to use the RUS R0805, this one. So we have the resistor over here. And when I type capacitor, you can see in the same Adafruit library, the same version of the capacitor, P0805, this one. One over here, there are two capacitors required for input and output. Now what we need is output and input terminal. So I'm simply gonna type terminal. Here, okay, now I don't think this library will be available pre-installed. So for this one, just go to Open Library Manager again. And if you use the online version, you can search for the library over here on the online. So you just need to type connector, and this library which I'm going to use is from the Fusion Electronics. You can search for this library in the online version. So what I'm going to use is this thing, screw terminals. The screw terminals are like there are one end is connected to the PCB, and in the other end you can screw your wires over there for better connection. So one for the input and one for the output. Okay, so now all the components are in place. Now we need to start the wiring. So here is the net over here, net part. Like this is going to wire all the components. So input is provided to the inductor, and this capacitor is also connected to this to remove any ripples in the voltage. The fourth pin of the IC and the fifth pin. Both are connected to the capacitor. Now the sixth pin is a not connect one, so we don't need to connect this one. The inductor gives the output to the diode, and the switch for the MOSFET. Sorry, switch for the MOSFET is connected between this one wire. Now as for the feedback will be given from the potentiometer. So the output of the potentiometer is going to go for the feedback, and the other output is going to go over here to the diode. This is the second capacitor, the output one, which is going to connect it to the diode, as in the primitive one I showed, and the output terminal over here. Now all the components also have the ground, so we need to add a ground also. So searching for the ground, just type GND, hit enter, and add any ground whichever you find. It doesn't matter over here. So one for the input, one for this capacitor, one for the IC, one for this resistor, for the capacitor, and for the output terminal. Now just hit escape whenever you're done. So again, you need to connect these grounds. Oops, that didn't connect. Okay, now instead of directly connecting the wires, there's another way to connect the two terminals. I'm going to show that. Like just place out a wire, just double click, it will end it over here, and place out another wire over here. Just double click, end. So you can also name the components in this thing. Just go to name, click on this wire. It's already given a random name. So I'm just going to hit ground. ND. So when you name wire this thing, like this component is also named ground. So if you name this wire as a ground, it will be these two will be connected. So yes, I want to connect these, and yeah, the connection is done. Okay, so now the schematic is done. This is schematic for the design. So now we'll move to the board part. We'll just go over here, generate to switchboard, this board, and it's going to ask if you want to create a schematic. Hit yes. Okay, so now this is the interface where we are going to make the board. Okay, any questions in the schematic part? Like anyone? Okay, no question. Okay, so here all the same buttons are there, except a few like routing ones. This I'll show when we do the routing. So in the free version, if you're doing, there's a limit to how much size the board you can make. So first we need to like decrease the dimensions. So this is gonna be our board over here. So this is the dimension layer. There are many layers in the PCB. You can see over here all the in the layer settings, like the top, bottom, pads, wires, unrouted dimensions. So the 28th layer is the dimension one, which is going to define the dimension of the PCB. I'll just make it short because we don't need much space. Yeah, this much should do. Okay, now to simply place the components in the board, just click on this thing, move. Just click on the components and just drag them over here. Now to rotate them, you can this thing, right click over here. Just right click and it will rotate. So I'm gonna just simply place this one as it is. I'll rotate and place this one. Okay, before that, let's go and name this. Let's save it simply. We'll go back to the schematic and let's name the components. That is easy to identify which component which is which. So just go to name, click on the component, and you'll get an option to name it. So this one is for input. You need to give this one a name. This is the inductor. So I'll just place a short one in. This one is quite clear. It says 34. This is the output terminal. Output. C2. This is our potentiometer. So I'll just name it pot. Ground C1. Okay. Now save it. Switch to board. So this is the input one. And another thing, we don't need this values of this thing. Like every component over here, it has a name and a value. So I don't think the values of any of the components is necessary as of now. So simply go to delete and delete this value. Anything else? Yep. Okay. And you can delete over here also. We'll do that later once we place the component. Okay, so drag and place. Delete the value. So input over here and output at this end. Place the inductor over here. The diode, I'll place it vertically over here. And the main IC. Yeah. And the last capacitor. Okay, so now we have placed all the components inside over here. I'll delete the name. Let it be T1. This can go okay enough. Okay, now one more thing. You can't make any changes in the connections in the board part. Like even if I try to delete any component, this can't be done. Or delete and wire connection part, this also can't be done. You need to do all the changes in the wiring and the components in the schematic part only. So in the board, you can't change anything except for the routing. Okay. Okay, now this button over here, the ratsnip. Now what this button does is it makes the the connections minimized. Like it makes the shortest possible connections between the components. So if I just hit ratsnip, you can see all the connections are changed. The shortest possible connections were made just now. So this is a very powerful one. Now, while making a PCB, a few things need to be kept in mind. Like you need to keep the connections as short as possible to minimize the cost. You need to keep the wires as much as less as possible. Like the manufacturer will cost you, will charge you. Like for every single wire, he'll charge you extra money. So all these things need to be kept in mind. Now, before that, there are many layers in the PCB. So and every component has a ground connection. So I'll make the top layer a ground. So just go to polygon. It doesn't matter how you draw the polygon. Just simply draw any shape outside the board. It's done. And now it's asking for the name which we give it. So I'll give it a ground name. I want it a ground. Now, at least now nothing will happen. But when I hit Racksnip, okay, now all the connections which were named as ground have been connected to the top layer. So this helps in this thing, the easy connections, and also helps in heat dissipation. Like all the heat, all the current is going to flow directly to the ground, right, at the end. So the heat, all the heat will be dissipated from the top layer itself. So routing is not very convenient in this form. So I'll just save, exit, and come back to over here. Okay, now we can do a better routing. So routing is nothing but making all the connections. So as you can see, like whichever this thing, the component was named as the ground, the part it has been connected to the top layer. So we need not make those connections again. So here, ground has been done. Again over here, ground has been done. So now we have a lesser number of connections available. Okay, so let's start the routing part. So what is this option? Route airbag. Now in Eagle, there are two options how you can route. Like Eagle also has an auto routing option, but I'm not going to cover that in this session. I'll just show you how to do that one. Like just go to edit, go to net classes and rules. Now in the rules, you define the rules for the routing part. So width of the traces, like the copper tracks that you're going to route, what will be the width of them? So let's say I'll make the width 12 mils. Now mil is a unit. Mil means 10,000 of an inch. So if you want, you can change the units always. If you want to change the units, just go to grid. And over here, the unit is mil. So you can make it to anyone, whichever you want, micron, millimeter, mil, or inch. I prefer mm. So you can just go to mm. Now, if you want the auto routing, so net classes define the rules. So say let's 12 mil drill. Drill is for wire. Like if you're connecting the top and the bottom layer, what's going to be the size of the hole that you're going to drill in? So let's say 10 clearance. Now clearance is the minimum distance that's going to be between two traces. Like you got to have a minimum distance so that the signals don't interfere. So when you define the rules, there is this option for auto router. So if you want to auto route the top layer or the bottom layer, how much effort do you want to put in it, medium, high, or low? Say let's say medium. And when you hit continue, it's going to provide you many options. Like when you hit start, there are at least 10 options that will be provided to you for routing. So the top router will also be will always be shown over here in the top, like according to number of wires and all. So there are different possible ways how you connect all the components. You can select whichever you want. But I'm not going to do this over here. So I'll just hit cancel. I'll open this thing again for routing. Okay, so we are going to manually route all the wires over here. Just go to route. And one more thing, like whenever making a connection, try not to make it as a sharp corner, like 90-degree turn. That is because whenever you go for the etching process, like when in the manufacturing, the 90 degrees turn, they may like give it a bit less straight, like the less width could come out after etching. So go over here for this option. So instead of, you'll have this 90 degree as a default one. So go for either 45-degree turn, or you can go for a smooth curve. Smooth curve is the best, but I'll show with the 45-degree curve. I'll switch back to mill for routing. So I'll go to 12 mil at least. Now mill, see actually the width of the trace, it depends on the amount of current that wire is going to carry. So if you have a heavy current, like if you're attaching let's say you're making a drone and the motor is going to be powered, so it requires at least 30 to 40 amperes of current. So obviously you need a bigger wire for that. And if, for small connections like over here, in like joining simply in the inductor and this thing, the diode, you don't need much width. So at least 12 mil should do. And if you're going to drill a hole, I'll keep it around 20 mil, and the diameter of it is going to be auto, like depending on the width of this thing. So let's start the routing. Now in the routing, you'll have two options, either top or bottom. Only two layers are available for routing. So I'll start off with the top layer. So whichever red color you see over here, like these pads, all these pads are the top layer pads. These on all these. So you can't connect a bottom wire directly to these pads. But in the connector for the terminal which I have given, you can see this green color holes. Now this means that you have an option to either connect a top layer or a bottom trace to this thing, to your terminal. So I have all of these pads have red color. So I'm just gonna go with the top layer for now. Okay, so like just click over here to start the routing and just drag and click again over here. Now this completed a trace connection between the diode and the IC. Now this inductor, you can see like two wires are mingling up. So I'll just rotate this one to make better connection. Now we have straight connections over here. I'll go again to the route, and this is connected to this part. So you can simply connect over here. Now 90-degree turns won't matter in this simple circuit, because there's not a lot of heat that is going to be dissipated on the turns and all. So you can make a 90-degree connection over here, but just keep it a habit to have 45 degrees turns. Okay. Now I'll switch places with these capacitors. Yeah. Also, this is going to be a better connection. Wires won't interfere with each other. And I'll rotate this potentiometer. Yeah. Now we have much better connection. Just again go to route. This capacitor is connected to the terminal. Done. Now this guy has a connection with the potentiometer, the diode. And the output is also connected to the diode. Yeah. Okay, so this guy has a connection over here. Done. Now, whenever you're connecting, the part which is to be connected gets highlighted. You can see over here. Potentiometer goes to the IC, the feedback wire. And this, okay, this also goes to the IC. It isn't this ground. Why did I connect the ground? I think I forgot to name this wire. Nope, it's named. Yeah, the ground connection is done. Okay, so now, yeah, in this part, the resistor is connected. Now you can see this one is far away, so I'll just go back. I'll rotate the resistor to make it a shorter connection. Done. Okay, I don't know why it's always showing me the ground air wire in the ISA net. Okay, now four air wires are left. Also, I'll show a way to how to identify which air wires are left for connection. So just go to layer and you can hide all the layers first, and only so the unrouted verbs will be shown in the 19th layer. So only one connection is left from the input. I'll show how to put wires also. So this connection I'll make on the bottom layer for the input one. So now a bottom layer is formed, which is of blue color. So different colors are given to all the layers. But now I can't simply connect this bottom layer to the red pad because it's in the top layer. So I got to add a wire. So without pressing anything, just go to select a layer, hit top, and it will automatically add a wire. And then you can connect it over here. So now all the connections are done. 3S wireless. Okay. Yeah, this part is left. So connect this one. And this. Okay, one more is left. Which one? Oh, I think I accidentally made another wire over here. Just delete this one. I'll reconnect this. Done. Okay, it's still showing another wire. Okay, I think in the schematic, nope, perfect. Wait, I'll just read out this one. I don't know why it's causing a problem. Still showing two errors. Okay, anyways, that won't be a problem. Yeah, so the routing is complete. All the wires are connected. So you can see a final design. Yeah, now. Also, I didn't show the group option. So if you want to move all the components of the group, just drag and select everything and just go to move. Just right click, hit control, and then you can move the group. You can see also control, right click. So you can move all the components over here, place them at origin just. Now there's also a way to add text or logos to your board. So just go to the text part, type whatever text you want to add, say ISA. Okay. Now this text is coming in the top layer, but the fill screen is not on the top layer. See all these layers over here, these are for the still screen. Like I told in the manufacturing, the still screen will be printed. So I can place it on the T place. This is the top still screen place where all the names will be printed. Say place it anywhere, wherever you want. And just hit escape. Yeah, so your PCB is done. You can also see how your PCB will look after manufacturing over here. So this is the top side, the bottom side. They only have one connection in the bottom side, which I made over here. And the potentiometer, the input and the output. Only these have through holes. Rest all are SMD components. So they're only visible on the top side. So they'll be printed on the top side. So you can also export this image and everything. Yeah. So any doubts in this thing? Okay, nothing.
If anyone has any queries, he or she can ask Anirudh right now. Okay, if there are no queries, I think we can wrap up the session. Thank you
If you
for
have any
your
other doubts, like whenever you're designing, you can just ask me.
right. I think you can give your VIT mail on in the chat box
Yeah.
just in case someone needs to mail you. Right. Okay. Thank you so much, Anurad, and thank you to each one of you for attending this session by ISA-VIT. We hope you learned something new today.
Okay. Thank you, everyone.
Thank you. You can start to leave the meeting now.